So hey everybody, glad to be here. Want to talk about how we can get teams of robots to work well together. I'm going to be using some unusual tools in some unusual way, and so I'm going to keep it kind of high level and give you kind of a high level understanding of how these tools work and how we're applying them to multi-robot collaboration. A lot of this work really dates back to 2010 when we were building teams of robots for the Magic competition, and that didn't work. Let's try that button. There we go. All right, so this was a team of robots exploring a building here in Ann Arbor. There's about 7 robots. They're sending messages to each other, and it more or less kind of works, right? They're exploring, they're filling the space, they're sending their information back to a command and control center. It's got more than 2 frames per second if you watch it on my laptop, but I guess over here, this is where we're at. But there's all kinds of terrible, terrible secrets hidden behind this video that we don't usually talk about, like the gigantic radio system with the base station with a human busily clicking away and trying to coordinate all of these robots. We made it work, but it wasn't always pretty, and this was one of the good cases. So really, this is kind of the motivation for today's talk. How can we build a system where you've got a team of robots that work well together when the environment is at least somewhat unknown and when communications are flaky, and do it in a way that's not going to drive your developers absolutely crazy? So there's lots of challenges that come up in here. Communications limitations are a big one. When I talk about low bandwidth, I'm talking about really low bandwidth. So I think bits per second of data traveling from one robot to the other one. If we've got kilobytes, whatever, right? You can make something work, but bits per second. Unpredictable lossy networks, that's a huge problem. Your radios could be at the edge of their communications range, or you could have a bad guy jamming your comms. Trying to figure out how to maintain those, make use of what communication resources you have is actually a really hard problem, especially when sometimes it might be gone entirely for minutes at a time. And then all the sort of standard computational problems that come up when you've got a team of robots. How do you get a team of robots to plan jointly, to split up the task in an efficient way? When you've got imperfect information, there's a partially observable Markov decision process buried in here. Managing computational complexity, and then trying to make the thing work, not just in the environment that you started off in, but to work in a wide variety of environments that you hadn't anticipated. So I'm going to start with a cartoon. This is sort of the flow of how a lot of roboticists, myself included, like to approach a problem. Someone gives us a problem that we want to solve. It's solving a maze in this case. So we think for a while, and then we have sort of a aha moment. Here's an algorithm that will solve that problem. So then I go off and we code it up, or in my case, I have my grad students code it up. And then, yay, we deploy it and it works. That's what we'd like to believe happens, but those of you who have built real multi-robot systems know that there's actually some more steps after that. So step 5, you realize that the world is evil, and not all the mazes that you were thinking about look like the one that you started off studying. You know, here's one with a bridge. Did you consider that there'd be overpasses? No. Did you think of doors that might be locked and there might be keys in there, or that might be made out of corn for some reason? So all of this, the infinite variation is really likely to make the method that you came up with in step 3 not work anymore. So no problem. We got a lot of smart PhD students. We send them off, we lock them in a room, and they come up with lots of ideas. This one works really well on bridges, and this one works really well here, and this one works on doors, and this one works on corn mazes for some reason. That was a joke. Tough room. But then we end up with this problem of how do we figure out which algorithm to use when in which environment? We don't know a lot about the world. We don't know about the communication structure. And so the common thing to do here is to maybe write some hand-coded logic that says, hey, you know, if the communications are really lousy and it's really hilly and there's bridges that go over the corn maze for some reason, then you know, use algorithm 17. But ultimately, this just leads to despair. It's really hard to build a system that's going to work in all these different conditions. And for those of you who know me, I dabble in autonomous cars a little bit. This is the universe that autonomous cars are living in. People talk about going out and collecting billions of miles of training data so that they can catalog all the weird edge cases so that they can write this thing that can anticipate all the conditions that a car might find itself in so that they can run the right motion planner strategy at the right time. And it doesn't work. So that's what we're working on. I forgot to start my timer. So that's going to run me over a little bit. So I want to introduce you to an idea a little bit. This first 5 minutes are free, right? So an approach that we've been taking in our lab for quite a few years now is called multi-policy decision making. Really the idea is to think about design of our systems in a slightly different way. So we've got a perception system just like everything else, but then we build a belief state about the world. So imagine that you're building a simulator of the world around you. Something that you're going to use in situ, live on the vehicle. So you're in the model, and you're in the model, and if it's a car, maybe you're a good driver, and maybe you're not so much. But all that's captured in the model. The geometry is in there for communications. Your belief about what your communication environment might look like is in there. And then you have a bunch of different strategies for how you and your team of robots might operate. And the way that we try to solve this problem is instead of trying to figure out in advance which policy to use in which condition, we just try them all in a simulator that uses our representation of the world. So there's a lot of live simulation going on in here where we try different approaches in the simulation and then score how well they work in the simulator and then elect the best policy for our robot or our team of robots based on what the simulator says. This is a really dumb idea. Based on writing a bunch of really simple control strategies and not trying to figure out when to run each one, but just brute forcing it. Right. So what we're going to see today, a quick review of how multi-policy decision making has worked in the past in some other related domains, give you kind of a feel for what works and what doesn't work. And then I'm going to apply this to communications. All right, so MPDM was born in the domain of robots operating amongst humans. And one of the problems that you have here is that there's lots of complexity, lots of structure. If you're driving around a hallway, you don't know what this person's going to do. There are sort of rules of thumb that maybe you should drive on the right if you can. But do you drive on the right if someone's in your way? Do you pass them if they're in a line? It's writing down the rules of what you should do when is nearly impossible. So what we did is, this is my student, Dan Van Meta, who wrote a bunch of very simple policies, sorts of policies that an undergrad can write in a couple-week project. One which is to basically treat the world as static obstacles and just do a conventional motion planner, right? Call it go solo, like basically ignore the rest of the world, just do your thing. Follow is a policy that basically picks another agent and says, I'm going to follow them. Is that agent going where I'm going? I don't care. I'm just going to follow them, right? So really slicing away a lot of different factors that a robot would ordinarily really consider first order, and just saying, hey, one thing I could do is I could follow Ben. It could work out. He could lead me to my death, but we can find out. And then stop, which is a real head scratcher. Undergrads can definitely write this one. Robot stops. So I'll give you an idea of what these things look like. The robot. Wow, with the frame rate here is really making this a little more difficult. But here you can see the robot plots a path around these guys and doesn't hit them. Yay. Okay. The frame rate is making this a little harder to figure out what's going on. Here's the robot that picks an agent and decides to follow it, this guy, I guess, and then stop, which stops. Oh, yeah, see, stopped. It stopped. That's ta-da! Thank you for your time and attention today. So you put these things together, and you get the robot's constantly doing these simulations and switching between the repertoire of policies that it has available. So each individual policy is really dumb. I sometimes call them like idiot savant controllers, right? They understand how to do one thing like follow Ben really well, but they don't actually understand the bigger picture of the different rewards that I'm trying to optimize against. But the simulator just keeps trying them and asks the question, which of these idiot savant controllers tends to do the best for me? And then, hey, that one seems to work out really well. Let's use that. And the frame rate's making this a little hard, but here you can see it starts off by stopping because basically none of the policies were leading to a good outcome. But then a path opens up, so it goes solo, and then as the world opens up, it maneuvers back around those other agents. This makes a lot more sense at more than 2 frames per second. Here's another example of this. How many of you have been around a robot as it's driving around, been like, this thing's annoying, it's jerky, and it's frustrating? It's not a rhetorical question. Let's do hands, right? Robots are annoying. This is a system that when you interact with it, it feels like a different universe. It's based on multi-policy again, and it's electing a new strategy about twice a second. And what you get out of it is not apparent at 2 frames per second, but really smooth behavior. Smooth behavior that's constantly changing what it's doing based on its models and predictions of what other agents are doing, and basically peeking 15 seconds into the future using its simulator to figure out which strategy is most likely to not run into people and get the robot where it wants to go. I can make these videos available offline. For now, you're just going to have to take my word for it. That's silky smooth. Okay, great. So now you're like, wasn't this talk about communications? Yes, it was. So let's talk about communications. When you've got multiple robots working together, you get a whole bunch of new interesting problems. So there's this sort of theory of mind problem that all of a sudden pops up. What do the other robots know? What would they do with the knowledge that I have? And this makes things really complicated. So let me describe this figure. This is a simple little grid world. We've got 2 robots. One robot starts over here. One robot starts over here. They're both trying to get to the same goal, but they both have different beliefs about the world because their sensors have given them different experiences. So this guy knows that these white cells are open and these are obstacles, and doesn't know anything about this area. And this guy knows that these are open, obstacle, and doesn't know anything about this. So now these robots are trying to work together to figure out what information should I send to get this to help the other robots get to their target faster. So imagine that you're robot number 2, and you happen to know that robot 1 is here. What do you think? What should you send them? So again, we're robot number 2. You know robot number 1 is here. You know the goal is here. What's that?
Go to it.
Yeah, go to it, right? Do you have any information over here that helps it, that's likely to help it? No, right? You know some stuff over here. And so, but sharing that, you can actually make a prediction that if you told this robot that there was stuff over here, it wouldn't change its behavior, right? So what would be the change to that robot 1's reward function? Nothing. So if the change in the reward function is 0, then you shouldn't send anything. That's pretty cool, right? We didn't have to try to figure out what is the reward associated with communication or communicating or information gain, which is sort of a proxy for usefulness. We're able to run the simulator and figure out how would an exchange of information actually change the behavior of the system, and how would that change in behavior result in a change to the reward function. That's actually pretty cool. Most people use like an information gain criteria where you say, hey, if I send this stuff, this robot's going to learn something about these grids and that has some inherent value. We say, no, it doesn't have any inherent value. How about this guy? Robot number 1 is looking at his universe, and he's trying to figure out whether he should send information to number 2. Maybe, right? So this, if he's imagining the robot number 2 plotting a shortest line path, might very well go through these black cells. Might go around, but there's at least some probability that robot 1 thinks that robot 2 will run into these obstacles. So by telling robot number 2 about these obstacles, we reduce the average time for robot 2 to get to the target, which improves our reward because we're using discounted rewards, which means that, yes, we should send it. Probably. That's pretty cool. Now, this gets a little more complicated because robot 1 doesn't actually know what robot number 2 knows, because if we could just share everybody's state, then we wouldn't have a communications problem, right? If we could just blast everything out, then we could just do joint optimal control and planning. So the reality is that robot 1 actually doesn't know what robot 2 knows. Robot 1 has a probabilistic distribution over the things that robot 2 might know. And so as it's running these simulations, it has to repeat its experiments. Well, what if robot 2 knew this? Now run the simulation. Does me transmitting information help or not? What if robot 2 knew this? And on you go. And so we end up doing a lot of simulations to basically marginalize over our uncertainty about other agents' beliefs. That's pretty fun. And it gets a little hairy. So we've got robot A is going to be modeling robot B's belief state. And of course, all these robots are using our favorite algorithm, MPDM. So robot B is also modeling robot A's belief state. So does that mean that robot A is modeling robot B's belief of robot A? And so on and so on and so on. And so, you know, the old joke about like there's turtles all the way down. On this pile of turtles are the corpses of many PhD students who have not been able to make this work. Not these guys are great. But one of the real challenges here is how do you sort of cut the complexity? How do you say the end of the turtles and be able to build this system and have it compute reasonable plans? Next slide. And so the idea is to come back to multi-policy decision making. And we have agents which have some policy. We don't know what the optimal policy is, but we can write down some policies. We can write down how they tend to communicate, what they should communicate. And without trying to figure out what A knows about B that A knows about B's A, we can just try things and see what works out. That's the idea. Substitute brute force for hard thinking. As I get older, that sounds more and more appealing. Basically, I already said this, so let's skip this guy. All right, so turns out we're not the only people who like working on these problems. Shaw's group at MIT basically did this exact same problem. And you've got these axes that basically say, what fraction of the information are you sharing? Right, so this could go out to 1, in which case you're sharing everything every cycle. And then, as a function of how much information are you sharing, how well does the system perform? And so what you first of all see is that the more information you send, the better you do. That sort of checks out. This particular approach was based on an information gain criterion, right? So that it's useful to send information if the receiver finds out something they didn't know before, which, as we just kind of talked about, isn't actually the right thing. It's maybe better than nothing, but what you really want to know is whether transmitting the information gets the job done. So if you run the same experiments with our algorithm, you get quite a lot better. Now, keeping in mind that this is a logarithmic scale on the x-axis, we're almost as good as communicating an order of magnitude more. So we're being much, much, much more efficient with our communication. And a lot of this comes down to figuring out when it's useless to send information. There's a comedian, I'm going off script here, it was a Simpsons episode where Homer Simpson invents the everything's okay alarm. It's like, it just goes off all the time, right? And what's the information content of that, everything's okay alarm, right? 0, right? So turn the darn thing off, right? So we turn off the everything's okay alarm and we get better performance. The other nice thing about the approach, though, is that we can actually go a little bit farther, and we can say, hey, rather than sending our whole map or not sending our whole map, so the baseline method sends the entire map at once. So the decision is, do I send everything or do I send nothing? With our approach, we can just add more policies that say, what if I shared a fraction of my map? What if I shared just my most recent observation? We can give the robot more choices of what it wants to communicate. And do we have to change the simulator at all? Or the algorithms? No, right? We just, in the simulation, the robots receive messages that informs their belief state, their behavior changes. They're all scored based on how well that information helps them achieve their objective. And we can just, it's very easy to extend the system in this way. And bam, take that, Julie. I like Julie very much. But we do really well. So lots lower communication, and we're much higher task performance. Now the problem, here's sort of the funny thing is I'm 20 minutes into the talk, I haven't actually gotten to what we're doing on this ARC project. So we're building up to it, but we're almost there. So the problem with this is that planning on the individual granularity of which grid cells am I going to share information about is incredibly expensive. Right? We've just made a massive computational trade-off. Sure, we save a lot of bandwidth, but boy, our CPU is just running on these simulators, marginalizing over all of our uncertainty about the world. So this limits the kinds of problems that we can solve. And if you noticed on the previous slide, you've got a 4x4 grid world, which Ben's smiling right now. Like 4x4 grid world's like, enough with the 4x4 grid worlds. So the question, this is the ARC proposal, what we're working on now. How do we solve longer horizon problems kind of using these methods? And so if the original multi-policy is essentially electing control laws that are outputting motor outputs and individual messages to send, and they're making decisions on the scale of 100 milliseconds with a planning horizon of 10 seconds, how do we get to something that looks more, oops, wrong way, this? So where the policies are macroscopic coordination strategies. The policy outputs might not be motor outputs, like how many volts am I sending to my left motor and my right motor, but more like where's my next goal? Like where in the world should I try to go next? The action timescale might take me 10 seconds to execute this policy output, and the planning horizon can go up substantially as well, hundreds of seconds. Now it starts to get pretty interesting. Waiting for the internet here. Oh, now I hit twice. It's going to ruin it all. All right. So here's the domain that we went with. It's basically a pursuit evasion game. We've got a bunch of robots that are going to chase a bad guy. In this case, this is the 3rd floor of the Bob and Betty Beister Computer Science Building. And one of the challenges here is that you really need the robots to coordinate in some way. If you don't have enough robots, the evader can just run circles, kind of like you and your nephew, sort of being on the opposite side of a table when you're playing tag and there's a table in front of you. Same thing happens in this game. This world, though, is massive in comparison to a 4x4 grid world. Now, we're still going to abstract a bunch of this away to make it more computationally feasible, but now we're scaling this up to something that starts to look and smell like a real environment, which is exciting because I like robots. So here's our abstraction. Here's the real world environment. We build a graph version of that world. Evaders get yellow dots and robots get blue dots. And so if you're noticing a Pac-Man theme, strap yourself in. There's more coming. So one of the big questions is, now if we're going to build a simulator that allows us to make predictions, how do we model the behavior of the Pac-Man, right? The evader. So there's lots of ways of doing this, and basically, we've run the gamut of really complicated, fancy methods. In this case, we're using something relatively simple, which is you basically got someone loitering in the building, and if they see you coming, they go the other direction. Otherwise, if you're not bothering them, they're content to kind of sit on their butt. Is that kind of a reasonable, accurate? Or they move randomly, right? So they kind of stroll around. Not especially smart, but you could have that on a military base or something like that, where you've got a bad guy who's snooping around, trying to duck away from other folks. So now the question is, what are the policies that we're going to allow our robots to check to follow? How many of you actually know a lot about the Pac-Man AIs? Okay. So this is, I'll give you the 30-second version because this is actually a lot of fun. This was one of my favorite 280 programming assignments when I taught 280. All of the ghosts in Pac-Man have a very specific policy. Right? They basically have a goal point that they compute in a deterministic way based on where the Pac-Man is and what direction he's heading in. And then they have a fixed motion planning strategy to get there. In this case, Clyde's strategy is basically always Clyde's, and Blinky's a little different, and Picky's, they're not switching their policy. But you've got a bunch of very, very simple strategies for the evaders that nonetheless kill basically all of us when we play Pac-Man. That's kind of an encouraging thing. So we have basically the same sort of thing. These are not smart strategies. Every time you got a chaser, a robot that comes up to an intersection, he picks the next intersection randomly, or the next hallway randomly. Pretty self-explanatory. Belief gobbler, this is not a term of art, but we like it. The basic idea here is that you've got a probability distribution over where the bad guy could be. And at every time step, you do a diffusion process on that probability distribution to try to imagine where in the next time step they might have been. So basically, we can't see the evader, and we just kind of assume that they're moving around, and our uncertainty glob around where they are just gets bigger and fuzzier over time. With the exception that if I go into a new grid cell and I don't capture them, then I know that the probability that they're in this cell drops to 0. So basically, you've got two processes running, one which is this diffusion process, which adds uncertainty to where I think the bad guy is, and this zeroing process based on where the robots are. Everybody with me? All right. Both of these policies are pretty dumb, but that's actually going to turn out to be kind of a cool benefit. So, all right. I need somebody to play real quick so you guys can see what the simulator's like. No hands. All right, fantastic. So keep in mind, I'll bring the laptop to you. You're good. Keep in mind that the evader knows where the robots are. So the bad guy, the Pac-Man, can see where the ghosts are, but the ghosts cannot see the evader. So I'll do this, and then do this, and there's almost enough contrast to see what's going on. So if you use the arrow keys, if it's not working, I might need to just hit reload. I'll just reload. Because, internet. Try it again. OK, good, it's working. So he's driving around with the arrow keys. He's controlling the yellow guy. And the blue guys are deciding on a macroscopic coordination policy between either belief gobbling or this random hallway selection. And the thing is that neither of these policies are particularly good, but the simulator gives them both power. They both behave differently, and so being able to pick the better of the two policies, even if both of those policies are pretty dumb, makes them not so terrible. So keep in mind, the blue guys can't actually see the yellow guys. Oops, we can scroll so that you can see where you are. I can't, apparently, but we're good. All right, you get the idea. 57 is actually quite good. So yay! But you get kind of the dynamics, right? So the blue guys, the good guys, are simulating what might happen over the next 100 steps or so, trying different strategies out. None of those strategies are particularly good, but we can see what happens as we switch back and forth between them. And there we saw anecdotally. Let's see what happens if we use science. And by science, I mean more CPU. All right. So this is communication probability. Yeah. So we've got we're doing a parameter sweep over how much communications is getting through, and then we see the score if the robots are not using multi-policy, but always using hallway patrol or always using belief gobbling. And what you see is that belief gobbling basically does better than hallway patrol, right? If you have to pick one policy. But the interesting thing here is that MPDM is usually selecting the right policy. It's selecting the policy that performs better without us having to sit down and write under which conditions you should use belief gobbling versus hallway. And so from a sanity of a developer perspective, there's something really exciting about this. If you are trying to extend your system, you want to give it a new capability, you can toss new capabilities into multi-policy, and let the simulator decide whether to use them or not. And if your policy is really terrible, like it just never works, it's not going to get elected. And so, think of multi-policy as basically a way of selecting the best available policy, and it makes building your system modularly a whole lot easier. All right, next slide. So that was that environment that we were just in was actually pretty simple because there weren't that many loops. Here's another environment which looks like a grid world, but actually, topologically, this represents a much more complicated environment. All these loops make a lot more space for you and your nephew to kind of chase around the table. And so here we've got the two different strategies. Hallway patrol actually does a little better than belief gobbling. So it's a reversal of the previous situation, right? So one of the key things here is that the correct strategy likely depends on both the environment and the communication environment, right? The structure of the environment, and it's hard to know those things in advance. And here we see a reversal. Previous slide, this was the other way around. So any predictions? What does multi-policy do? Yeah, so I mean, what we'd at least hope is that it picks the right one. But what actually happens is it does better than either of them, which is pretty cool. Why is that? Because it gets to change, yeah. So Ben's doing this. It gets to change back and forth. So depending on what the exact current estimate of where the bad guy is, NPDM is dynamically switching between these policies. And so even though, on average, belief gobbling kind of sucks, sometimes belief gobbling is just the thing to capture the bad guy. We didn't design it that way, but sometimes that happens to be the case. The different behavior that you get from that happens to be a good choice. That's pretty cool. I like it. Hopefully you like it too. All right, so we're in the wrap-up phase. Here's where we were. We realized that the world is evil. Lots of things, lots of different environments. Think about how the strategies that we had in those two worlds led to two algorithms that switch places in terms of which one's better. So those are our two ideas. And instead of writing down in advance which policy we should use when, now we use multi-policy, and now we have happy developers. That should go out on that slide. All right. So programmatic stuff, we're actually in year one of this project, just kicking off sort of the basic work on building the simulation stuff for the communication-based planning, getting our robots up and running, and we've got lots of fun stuff planned in the future. And meanwhile, we had Cameron's back there, one of our undergrads over the summer, helped us refurbish 4 of our large robots. And now we have 4 robots that are ready to go and do this. And stay tuned. Pretty soon in Bob and Betty Beister building, you may be running for your lives from teams of robots that are conspiring to capture you, which would be a lot of fun, wouldn't it? That's it. Thank you.